Hello and welcome again to my Physics Online video lecture series. In today's video, we're going to be talking about Kepler's laws of planetary motion. So these are the laws that basically come out of and maybe underpin the Keplerian model of the solar system. In other videos, for both this course and other courses, algebra-based physics, calculus-based physics, physical science, etc., I have come time and again to talk about different models of the solar system that led up to the Kepler's model. So what are the laws behind Kepler's model, or what observations did he make and what conclusions did he draw from them? Well, the first of Kepler's laws, and this is the one that makes his model quite different than all the other models up to that point, is that rather than having circular orbits, or even circular orbits that have, let's say, retrograde motion, or that have circles within circles, if you will, in Kepler's law, everything has elliptical orbits. So instead of having the sun or a planet, such as the Earth, at the center of the solar system and everything then going in circular orbits around whatever's at the center, in Kepler's system, the sun is at one of the two focal points, one of the two foci of an elliptical orbit. And so our planets, rather than going circular around the sun, travel around an elliptical orbit like this, with the sun being located here, for example, at one of the two foci. And so your planet is basically just moving counterclockwise around this ellipse. I'm not actually sure historically whether Kepler stated explicitly within his laws that the solar system has a counterclockwise orbit as viewed from above, or from the north, above the north of the Earth or whatever, but they are counterclockwise orbits. The law itself says that the sun is at one of the two focal points of this ellipse. And so instead of having a radius of orbit, you actually have a semi-major and semi-minor axis. So this would be axis A, this would be axis B, the minor axis. As it turns out, most of our planets, including the Earth, have orbits that are near circular, but they're not actually circular. So Kepler's first law is that the planets have elliptical orbits. So Kepler's second law is the equal time in equal area in equal time law. Basically, the way that this works is if I have the planet and it moves from here to here in some amount of time, I can draw a little dashed line from the sun to the planet at each of those, and this right here would represent the area swept out. And then somewhere else in its orbit, maybe it sweeps out from this location to this location, and so in the same amount of time. So maybe this represents like a week or something like that, and this right here represents another week. Then these two areas must be equal to each other. So delta T1 is here, delta T2 is here, area 1 is here, area 2 is here. Essentially, delta T1 over delta T2 should be equal to 1 because it's an equal amount, and that would be equal to area 1 over area 2, which is also equal to 1 here. If we doubled the amount of time taken, then this actually still holds true, by the way, because if I double the amount of time, then I'm going to sweep out two area 1s. So in some sense, this right here is the mathematical statement of Kepler's second law. Kepler's third law is the one that we actually use the most for kind of like solving problems, especially in algebra-based and even like conceptual-based physics classes. Kepler's third law says that the period squared of the orbit is proportional to the average radius cubed of the orbit. So again, if I have my orbit like this, and I've got my sun over here, and I've got my other focal point over here, my average radius is basically like this. It's a near circular orbit. And so the period t represents how much time to complete an orbit. That's called the period. So period is how much time to complete one cycle, essentially. So in this case, it would be one complete orbit around the star. So this is Kepler's third law, and it's actually from Kepler's third law that Newton essentially synthesized his law for universal gravitation. And that, of course, will be a topic for a different day's video, the law of universal gravitation, sometimes called the Newtonian synthesis. So those are Kepler's three laws of planetary motion. Those are the laws that basically come out of Kepler's model for the solar system. Kepler, for what it's worth, basically made use of Tycho Brahe's observations, and of course we talked about Tycho Brahe in any of those other videos that I've mentioned about models of the solar system, because there was the Tychonic model in which essentially Brahe's model was that the Earth goes around, the sun goes around the Earth and everything else goes around the sun. And so Kepler used his observations and said, there's still a little bit of this. We can simplify a little bit more if we make use of an elliptical orbit that's nearly circular and put the sun at one of the two foci. So I've drawn the two foci far apart in all these drawings, but in actuality, they should look more or less like this, where they're very close to each other relative to the size of the circle. So then you get Kepler's laws, and then from Kepler's laws, Newton was able to then build his synthesis of Newtonian gravitation. All right, as a brief example for this video, we have Jupiter. Jupiter has 4 Galilean moons, Io, Europa, Callisto, and Ganymede. So the two innermost ones are Io and Europa. And so Io has a mean orbital radius of 422,000 kilometers, roughly, and an orbital period of 1.77 days. And Europa has an orbital period of about 3.55 days. So we want to know what is the mean distance between Jupiter and Europa. So again, using the third law, which says that basically that t squared, the period squared, should look like the cube of the radii. We would write something like this, where I'm using I for Europa, for Io, and E for Europa. And so the mean orbital radius should look like the ratio of these two periods, T Europa over T Io, to the 2/3 power times the orbital radius for Io. So that is 3.55 days divided by 1.77 days to the 2/3 power times 422,000 kilometers. Putting that into a calculator, we get that the mean orbital radius for Europa is about 671,000 kilometers. And that's it. So that's all that I'm going to do in today's short video. Thanks for watching. I hope you learned something for it, and I'll see you in the next video.